So the Milky Way. It is a real shame that we haven't at least had one really good, complete power outage this semester so you guys can see the Milky Way. Because that's about the only way you can see it from Cleveland, right? You have to be somewhere where there is very little light. In fact, no light at all really helps. And then you can begin to see the path across the sky that is the Milky Way. All right? So you guys have probably seen all these picture photos that people do online, similar to this, where they've got a really nice picture of the Milky Way, right? This is not one that they just went out and clicked and took. Right? There's way too much light in this picture to actually see the Milky Way like this. This is a photo where they actually did a long-term exposure to get the Milky Way and then added in other bits and pieces, right? So they cheat a lot. But there was a time when you could see the Milky Way, right? It was the river of the stars. And there have been a few times when I've seen it, depending on, because I was in the right place, the right time, humidity was low. And once we had telescopes, we began to understand the Milky Way, right, is just millions and millions of stars. It's called the Milky Way. Why? Because it was just kind of a faint, milky strip across the sky. It wasn't regular, it was a little bit back and forth. But when you have a telescope and you start looking, you get to see, oh wow, this is made up of a bunch of stars. A lot of stars. So our Milky Way is a galaxy, it is a spiral galaxy. And it is sorting out that we were in a galaxy, it took a while. Sorting out the shape of our galaxy took longer, right? If we had a uniform distribution of stars, everywhere we look it'd be kind of the same. That's not what we see. Right? We don't see a uniform distribution, we see this area where there are a lot more. If you really want a good look at the Milky Way, Australia is a good place to go. Because the Milky Way is there's more of the Milky Way to see from the southern hemisphere than the northern. 1748 sketch of the Milky Way. Right? Not the most accurate. Not sure what I would call this, other than not the most accurate. But it's really actually hard to sort out, right? Once we began to understand a little bit more, we started to get the size a bit better. First, as always, we began with we're somewhere near the middle, because we always start things that way. Then we later find out, oh, we're not in the middle. Okay, we're off to the side. And the reason we kind of thought we were in the middle is that between us and the center of the Milky Way, there's a lot of dust. Right? And so even though the center, this big bright center bit here, has a way more stars in it, it doesn't necessarily look all that much brighter, simply because there's a lot of interstellar dust between us and it. So, this is not a picture of the Milky Way, right? Not a picture of the Milky Way. This is a drawing or an estimate of what it would look like. And so we are about 30,000 parsecs wide. We're about 2/3 of the way out. Early on, we began to assume that we had the spiral arms before we had more direct evidence that there were spiral arms. Because when we look out in the universe and we see other galaxies, if they are roughly disc-shaped, like ours. Now we know ours is disc-shaped. Why? How do we know ours is disc-shaped? This is a pretty straightforward logic problem, right? Because all the stars, if you're scanning across, you guys are disc-shaped relative to me, right? So as I scan the room, people, no 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 people, people, right? So there's a narrow band. It wouldn't be the Milky Way if we weren't disc-shaped, right? That band would spread out quite a bit. So if we're in a big, like if we were in Job's, we are in Job. If we're in the main auditorium in Job where the seats rise high, you guys get spread out vertically more, right? Because the seats don't rise high in here, you're in a pretty narrow band. When we look at the Milky Way, we know that we are a disc-shaped galaxy simply from the fact that the stars are in a narrow range as we look at them, right? Every disc-shaped galaxy we see out there turns out to be a spiral galaxy. And so we began looking at, okay, is there direct evidence that we're a spiral galaxy? Can we figure that out? So, one of the things that happens in spiral galaxies is pretty cool. It's all because of orbital dynamics. If we could take a picture of this every million years to see the rotation in the galaxy, you'd see that the interior is turning faster than the outside, right? The further away you are, the slower you're going around. The closer you are to the middle, the faster you're going around. And so this swirling appearance is the result of rotation over a very long time. And the arms would slowly extend more and more, or get longer and longer and wispier, because as you get closer, those stars are moving around faster. Now, near the middle, it gets pretty crowded. You know, out where we are, we have about 0.003 stars per cubic light year, which means the odds of having a star in any cubic light year of space near us is pretty low, right? You got a 0.3% chance. You get near the center of the Milky Way, 10 million stars per cubic light year. So, if we were near the center of the Milky Way, you could get a sunburn from the starlight. Because there's so many stars in the sky, it would never get dark. Right? Yeah. Right? So many stars in the sky, it would never get dark. The other thing, when we look out there, one of the things we try and do is begin estimating what is the mass of the Milky Way by looking at all the stars and getting an estimate of the number of stars. We found out dust is about 15% of the mass. Most of the galaxy we can't really see direct on because it's behind a bunch of dust in the nucleus here. As I say most of the galaxy, I mean most of the mass of the galaxy is there in the inside. But we do look at it with radio and infrared, right? So in other spectrums, in other parts of the spectrum, we can see all the way to the core. We can actually begin to map out the structure of everything using the other parts of the spectrum. A couple other features our Milky Way galaxy has that we see around other galaxies too. One is there's a halo, right? And so there's a region around it. It's a lot like, what does this remind you of? In terms of, you've got a big central region, you've got a bunch of stuff swirling around here, and then there's this more diffuse area out here.
Our solar system.
It's a lot like our solar system, right? It's a lot like our solar system. It's the same sort of dynamics going on a much larger scale, right? And we have out here, we call these globular clusters out here. These are groups of stars that are out there orbiting around our galaxy. They're part of our galaxy, essentially. These are kind of like the comets and Eros and Sedna and some of the other planets, or dwarf planets, that are out there orbiting really odd orbits around our sun. Our galaxy has those same things. Little globular clusters out there drifting around, orbiting our galaxy. And then right in the middle, right in the middle where the majority of the mass is, there's this bulge. And we've got pictures of other galaxies where this is very pretty. We can see them edge on, we can see the bulge. So it is gravity that holds all this together. Again, if you're in here, if we were, if we could communicate with them and we had neighbors over in the next spiral arm, well, they're moving faster than us around, and so they would go out of range for us eventually as they moved around faster near the middle than we're moving around on the outside. Right? How massive is the Milky Way? Right? 2 times 10 to the 12th times the mass of our sun is all the mass in the Milky Way. So 10 to the 12th is, let's see, 10 to the 6 of millions. This is 2 million million, right? 2 million million, or 2 trillion times the mass of our sun. Now, we don't see all of this, and this is one of the current things that we're trying to work out in cosmology, is we've discovered that if you add up all the mass we can see, right? If you add up all the mass we can see in any galaxy, and then you look at, based on how the material in the galaxy is moving, how much mass there should be, we find out that we come up short. The reason we come up short is something that we now believe is out there called dark matter. Right? And dark matter is a version of a particle or particles that we've not yet discovered yet, and B, they do not interact with, emit, or otherwise show us any photons in any way. Right? So we can't see dark matter. Dark matter is really a bad term for it, because if I put something dark between you and me, it will block me seeing you. It's really invisible matter. Right? Dark is kind of a bad, dark means something different to me than it does to you. Right? And so it's really invisible matter. It's stuff we cannot see. We cannot observe in any way other than the fact that it interacts gravitationally with everything else. And gravity is the weakest force out there. Assuming that our sun is kind of average, there are about 100 billion stars out there. Right? 100 billion stars in our galaxy. Looking at our galaxy, the oldest stars seem to be about 13 billion years old, and here's a better picture of what the Milky Way looks like, in that it's just sort of this faint white glow behind some stars. So we look at the stars that are out there, we look at the distribution of the masses, and since mass determines the life cycle of a star, we can start sorting out how the Milky Way is evolving over time, right? A galaxy with only big, massive stars, all those stars are evolving quickly. Remember when we looked at the lifetime of massive stars, they're shorter than the lifetime of stars the size of ours. And also, how fast are they created plays into what are the dynamics of the Milky Way or any galaxy for that matter. So, looking at this, it looks like 7 to 8 stars per year get created in the Milky Way. No, it's a lot of space, right? Most of this is going to be happening in regions of the Milky Way where there's a lot of material. You get out to where we are, out in the outer spiral arm, right? The, what did Douglas Adams call it? The unfashionable end of the galaxy. You get out here, where there's not much stuff, and it's not going to be happening. It's going to be mostly in the interior. Most stars turn out to be dim, cool, red dwarfs. So most stars in our Milky Way are smaller than ours. The average mass is about the same as ours. And then really big stars in our galaxy are rare, right? A lot of brown dwarfs out there. Now, let's see, where was Jupiter? No, Jupiter wasn't that close. I think Jupiter, if it were about 50 times bigger, might get up into this range to be a brown dwarf. Okay, so when we talk about the stars in the Milky Way, we talk about two distinct populations. The stars that are in the disk, right? These are young, right? These are generally young stars. They are ones that have been made in the process of making the galaxy. Right? In the process of putting the galaxy together, these stars were created. They tend to be bluish, concentrated out in the arms. Our orbit around the Milky Way is almost a circle, just like the planets around our sun, right? Indicating again that we formed as part of our sun, formed as part of the formation of the Milky Way itself, right? Some heavy elements like our sun. Then there are these population 2 stars, right? Again, this looks like the wacky dwarf planets and planetesimals that are orbiting our sun at really odd angles and distances, right? Well, it turns out these stars that are out here going around the center at odd angles and going out much further in those directions than anything else, those are old. Right? Those may have been stars that were around, that formed on their own before our galaxy. Right? And there are things that are simply caught up in the gravitational attraction to our galaxy. They also not much in the way of heavy elements. So this, of course, all other things. Population 1 and population 2 stars, there's no real clear, easy boundary to say, yeah, this is that, the other is this one, right? Kind of like Pluto is on the edge of, do we call it a planet, do we not call it a planet, right? There are a lot of things around the edges that are hard to say they go one way or the other, but we can divide those up into little subdivisions, right? So Pop 2, older stars. Pop 1 are still the stars that are forming today, right? So when we talk about in the Milky Way, 7 to 8 stars are born a year, those are all population 1 stars. And it is the population 1 stars that we actually observe in trying to map out what is the structure of our galaxy. So, just like planets have moons, right? And collect material around them, we have globular clusters out there, star clusters, even within the Milky Way, where there are groups of stars that are traveling together, right? And they're rotating about a common center as that common center goes around the Milky Way. Just like Jupiter and its moons are rotating around a common center as Jupiter and its moons go around our sun, right? And so there are clusters of stars out there. Those get divided into 2 broad categories: open clusters and globular clusters. And open clusters, a few hundred members, right? The Pleiades, or the Seven Sisters, is an excellent example. And I don't know, I'll have to look and see where the Pleiade is right now. It's pretty cool because when we look up in our sky and we see it, we see a single star. And then when you pull out a good enough telescope and you look at it, you see 7 stars. Right? Because they're a cluster, they're all close enough together. These open clusters lie in the same disk, so they're part of those young stars forming in the Milky Way itself. And about 20,000 currently exist, right? And a lot of them are behind dust and things like that, so we look at those things other than the visible spectrum. So because gravity, there's a gravitational attraction between this controller and your pen, and your bottle of water, right? You know, gravity doesn't discriminate. If you have mass, gravity is attractive, right? And so, so we get these clusters, and then we get clusters that are sort of super clusters together, traveling through space. They're gravitationally attracted to each other. All of this, the substructure within the Milky Way, is just a matter of you get clumps. Right? You get clumps of material because of gravity. These are just images of open clusters. And these are groups of stars within our galaxy that, again, the Pleiades, if you look up in the sky and see them, you actually see a single dot. And when you look at the telescope, you see that it breaks apart into multiple pieces. All right, globular clusters tend to be bigger, tend to be more on their own. And by more on their own, they are out there circling around the Milky Way, going further out. They're not within the arms, right? They're not within the arms. They're out there moving around, orbiting around the Milky Way in a different way. And they look more like solid balls of stars. There are more stars in them. The open clusters that are within the spiral arms tend to be population 1 stars, young stars, right? Bluish. The globular clusters orbiting out there away from the arms of the galaxy tend to be population 2 stars, older, redder. All right. So, this is a great picture of interstellar gas. So the space between stars is not empty. Right? We think of it as empty. But over really long distances, it's not. In some regions of the galaxy, in some regions of space, there's a lot of dust. This is a great picture of a galaxy where you can see the bulge in the middle. You can see the halo around it that is, other material, other stars that are out there. And you can see this galaxy still has a significant ring of interstellar dust going around it. So most of this dust is in the galactic plane. It's not what you would call dense, right? A few gas atoms per cubic centimeter, whereas air is 10 to the 19 atoms per cubic centimeter, so it's not nearly as dense as air on the Earth. But it adds up over long, long distances. We can actually figure out from what the intervening gas does to the light of a star what kind of material is in it, right? We can figure out what kind of material is in it by what light it absorbs and what light it lets pass. So one of the ways we study this gas is we look at stars that we've managed to figure out what that type of star is, and we look at what the gas between us and it gives light on its way. Right? And these absorption lines tell us what kind of atoms and what kind of molecules make up the gas. So they tend to be like almost everything out in space, mostly hydrogen and helium and then a little bit of heavier stuff. Size is very small, right? It's very, very small. Your hair is about 10 microns wide, right? Pull out a strand of your hair. Your hair is about 10 microns wide. Well, not yours anymore, but yeah. But most of us, yeah. What little I have left. 10 microns wide. So dust particles out there tend to be out about 1/10 of that, down to 10,000 of that. Right? So down to really small. We can also look at light that gets scattered off of the dust, right? That's what we're doing when we see nice. That's what we see when we look out there and we see the light shining off of the dust. We're looking at the light scattering off the dust, right? This is like sunlight scattering off a cloud in the sky. When you look up and you see the red cloud, well, is the cloud red? No, cloud's not red, right? It's the sunlight coming off of it that's red. So we do the same thing with dust clouds. We look at the sun that reflects off of them, and that actually tells us even more about the kind of material that makes them up. So scattering helps if the wavelength is small. Right? And so this whole bluish end of the spectrum is where we usually see them.
I don't touch it and it does that. I really didn't touch it.
Right? And scattering is when we get a blue sky. Scattering is when we get red sunsets. So because the blue light tends to scatter, the red light is what makes it through oftentimes, and it makes stars look redder than they actually are. And then there are some regions where we see something like this, right? And this tells us, usually tells us in the visible spectrum, we can look in other spectrums and see stars there. We look in the visible spectrum and all we see is this. This tells us there is a nebula through here that is dark enough to obscure all the clouds behind it. All right? So, one of the problems this causes for us in astronomy, right, is that because our galaxy has a band of dust that we're about 2/3 of the way out. There's dust all around us in the galactic plane. Because our galaxy has a band of dust, when we start doing cosmology, looking at the overall structure of the universe, we have an area where we can't see due to our galaxy. Right? So we have trouble mapping some parts of the universe because of that. This is a great picture of starlight reflecting off of a nebula, right? So you can get all these beautiful, you can see the nebula because of the reflected light. And this is another thing. Have you guys ever been to the Hubble Space Telescope's website? No? Hmm? The Hubble Space Telescope website. Okay. We're going to have to show you that. So, once you start looking at these gases, a lot of the really beautiful pictures we find in space, or get from space, are due to interstellar gases. Right? Like this, light reflecting off of interstellar gases. We get some nebula that are actually emitting light, and they're emitting light because there's some star nearby that's getting them excited, and then they re-emit that energy. Basically, these stars, there's a star nearby that irradiates the gas then gets excited and re-emits energy in the visible spectrum for us to see. And this is when we get a lot of the really just gorgeous things going on out in space. It's kind of like, that's actually what, this is exactly, this is exactly the same process we use for fluorescent lights. Right? In the fluorescent lights, we have a little, at one end of them, we have a little device that excites the gas in the fluorescent light at a different frequency than visible light, and then the gases in the fluorescent light re-emit that energy into visible light. Right? So this whole process here is exactly the same as the fluorescence we use for fluorescent light. And also, why they get the colors they do, right? This is the same thing used in, when you look out at the store signs that use the old glass tubes and neon and argon and things like that. It's the same thing. There's a gas that we're exciting that emits light depending on what kind of gas it is. So if we look out there in radio spectrum, we can map out where different where different stars are in the radio spectrum, which lets us see through the clouds. So we can peer through the clouds using the radio spectrum, and we can map out where the stars are, and they line up, right, roughly along spirals, kind of confirming for us that the Milky Way is in fact a spiral galaxy. Okay. There are other kinds of emission we use. One of the emissions we talk about all the time is when an electron moves into a higher energy state and then goes back down. Another emission is just when you flip an electron over relative to the proton. Electrons and protons both have what's called spin. It's not quite the same as spinning around. So we look at all these radio emissions out there and we find, you know, where there's molecular hydrogen, where there's OH, all these different molecules that emit radio spectrum radiation. Yeah. You guys know this one, right? That's out in space. All right, so just like the planets go around the sun in their own little orbit, we have our own orbit around the middle of the galaxy, right? It's ours. There are other stars going around in different orbits near us. Stars formation happens when new gas gets sucked into the galaxy. New stars tend to be bright, right? New stars tend to be bright and they make everything light up. When we look at how these things form, one of the things that one of the models suggests that as an interstellar cloud comes through and enters an arm, it gets compressed and begins to collapse and begins to form stars, right? Just like if you're cruising down Highway 8, Sunflower Road, right? And you're in a line of traffic that's really spaced out, but then you hit 61, what happens? You get all bunched up together as you go through 61 because of the cross traffic, right?
Yeah.
I'm not touching it. I really didn't touch it. It has some water damage.
Right? So, the glass cloud comes through, it runs through the spiral arm, things clump together and it begins to form stars. Okay? Hopefully this won't happen as you go across 61, but one of the things that happens as we begin to try and model it out is that stars help create other stars. And so once you get one going, it helps compact gases in the region around it to create more stars, give them a little bit more energy by illuminating them and things like that. And so there's this process that goes on of getting the whole galaxy forming and getting star formation going.
So how does star get bigger and bigger?
How does it get bigger and bigger and bigger?
Yeah.
There's got to just be enough material in the area to pull in and form the star, right? If there's more, if there's enough material to keep pulling in material. Yeah. All right. You know, we're trying to figure out how big the galaxy is, and they use a lot of different methods. This tells us we're about 7 kiloparsecs from the center of the galaxy. It is, it's a big place, right? There are globular clusters all around. The geometric center of the globular clusters kind of tells us where the center of the galaxy is. You know, if you use that method to look at it, we're about 8.5 kiloparsecs from the center. You know, the thing we can't do is go take a picture because the distances are just too great. But at the end, we get to, the galaxy itself is about 80 kiloparsecs wide. 80,000 parsecs, right? A parsec is about 3 light years. If we go and use Kepler's law and try and figure out how fast we're going around it and how long it's going to take us and things like that, what we get is the sun's orbit is at least, the mass in the middle is at least 10 to the 10th solar masses. And if we begin to look at what is the speed of everything out there as we look through the spiral arms, so we can measure speed from Doppler shifts, right? We can begin to see some of the structure of the galaxy, of the galaxy as it goes out. When we look at the speed of everything, of our local group of galaxies as a reference frame, and we look at the speed of globular clusters, what we find is that there has to be a dark matter halo that goes out to about 100 kiloparsecs. Right? So the galaxy is at 80 kiloparsecs, out to about 100, there must be dark matter. And dark matter, again, should think really invisible matter. Matter we cannot see, right? All it does is have gravity, and that's the only way we interact with it. We look back at the center of the galaxy using X-rays and radio telescopes and gamma rays. Gamma rays are a little harder, but gamma rays. It's bright, right? In the X-ray spectrum, in the gamma ray spectrum, radio spectrum, it's bright. A bunch of stars packed in, a lot of movement in the middle of the galaxy. And really deep in, right? Really deep in, there's a core that's only 10 AU in size, right? So how far out is, let's see, Neptune is out at 30 AU. Uranus was out at what? 11 AU? Something like that? 12 AU? Right? So inside the orbit of Uranus, right, is a core to the galaxy. And that core is an extremely strong radio source, and we believe it to be a black hole, all right, that's 4 times 10 to the 6 times as massive as our sun. Right? This black hole, we see we see in other galaxies. I don't think our slides have it. Okay, all right. So there are a lot of different ways, a lot of different reasons for believing it there. It's there. One is that there's this very intense, very small source of X-rays, right? The other is from the